Ladies and gentlemen, welcome to the stream. There are 14 of you here. Hopefully we will pick up a couple more stragglers. Ladies, forgot to turn off my sound on my monitor. All right, so project is due. End of the semester, try and get it done by the final exam. I think that's pretty reasonable. If you can't, submit it by the end of the semester. If it's wrong, what are you gonna do? Stuff happens. Okay, so today is, I think, the second to last class, right? When is the exam? When is the final exam? UMBC registrar. Um, 2016, main campus. Our class is Monday, Wednesday between a 2 and 3. So our exam is Friday. At 1 o'clock. The final is not going to be, the final will be in the usual room, Friday the 16th at 1 o'clock. The final is actually going to be pretty straightforward. What I would like to test is, do you understand the general concepts? So I'm going to make it easier than the midterm was by a pretty substantial amount. And next class, we will review for the final. Yeah, that seems good. And that'll be it. You'll be done. You'll be done with AI. I don't know. Final will be cumulative. It will cover everything. What I have in mind for the final are things like proposing Stephen, okay, if you can't find the difference between liberal and conservative, you don't have to add an article to the corpus. Just treat them as two data sets and see if you can find out something interesting or different between the two of them. I lost my train of thought. So next class, we will be in the room. We will be doing exam review. In general, I'm going to just ask you about general concepts. We're going to not do very much math. It's going to be like maybe 8 pages of short answer or something. Like, what is genetic algorithm? What problem does genetic algorithm solve? What is reinforcement learning? What problem does reinforcement learning solve? And I also need to remember to put all of the slides up. Let me add that to my list. Slides up. Maybe we'll draw some pictures, and maybe we'll do the review at the ice cream place. Let me think about that. All right. Yes, I will give you a topic list. I mean, the topic list is literally everything we've talked about, but YOLO. All right, let's talk about the topic today. Final is, I believe, Friday, the 16th at 1 o'clock in our normal classroom. All right. So let us switch gears real fast. So what did people think of the lecture last class? Was it interesting? Florian, I don't know if he's a super great speaker, but he actually totally knows about deep learning stuff. Hopefully you guys are like, ooh la la, so cool. And then go do careers making machines creepily intelligent. Awesome. I'm glad to hear one person enjoyed it. All right. So deep learning is sort of his jam. This is going to be sort of the thing that I am interested in. When I was okay, so you're gonna learn a little bit much about me, but when I was a wee child, I didn't have any friends, so I was like, there must be math that will get me friends. And I started doing projects analyzing social networks between different humans. And so I started my thesis in 10th grade, my master's thesis, and sort of worked on it intermittently up until my master's. And it was link prediction in social networks. No, I was too dumb for the math club of my school, actually. So one thing we haven't really talked about is graphs that have a time component, a graph that changes over time. However, that's a huge thing. Like if you think of your relationships with your friends, they evolve from year to year, and they can evolve rapidly. Breakups. Actually, a great way to talk about changes in social networks are breakups, right? Because you have two heavily linked people, they break up, and then, do we have buzzing issues? All right, well, while I figure that out, you have two people and they break up, and suddenly, like, all of their friends have different relationships, like, everything kind of changes, right, in that social network. So buzzing, let's see if the buzzing is still here. Buzzing should be gone by now, but that's, All right, so let's see if that's gone. I'll wait for the chat to catch up. Other networks that change over time, internet traffic, right? Like some routes through the internet don't always exist. Some things will not always forward packets. You can imagine an organization as a network that changes over time, right? The people you interact with, the people whose projects you're on, are going to change. Like departments get reorganized, all sorts of stuff like that. So one of the things we would like to be able to do is predict what these changes are going to be. And predict in what ways they're going to change in sort of natural networks. And maybe figure out the best way to change them if we can control them. So the application that always springs to mind first, because is kind of a warfare application or terrorism. If you have an enemy group or an enemy like terrorist cell, being able to predict who will connect with who, or even if you just have criminals. Actually, fraud is a really good example. If you have a bunch of people who are doing fraudulent things, and maybe two of them connect, they will probably share information. They can actually spread fraud throughout the graph. Certain ideas are actually contagious. So it's good to be able to figure out what relationships people are going to have to see how those ideas spread. On a more benign note, Facebook friend suggester. Ugh. Facebook uses one of these algorithms to recommend friends to you. There are, like, you can use it to measure when internet traffic will pick up or go down. This kind of makes sense to people, like why this is an interesting application. Basically, we have any graph, and the edges are coming and going. And there's some underlying pattern to how they're coming and going. And we want to predict this. And actually, I'm going to kind of nerd out here a little bit, even more than usual somehow. Graphs tend to follow a really similar structure. Like all graphs follow similar underlying rules, whether it is human social networks or
graphs of like the internet, anything like that, follows certain underlying rules that we can sort of abstract and utilize to make predictions. So there are two kinds of temporal graphs that we talk about. Some temporal graphs only allow the adding of edges. So if you think about how Facebook used to be when you never unfriended anyone, a friend on Facebook is basically an edge that once it is there, it is very rarely removed. Or imagine you co-author a paper with someone. There's this really popular co-authorship data set where people add links whenever two people write a paper together. That's what causes a link to be added. I think these are not as interesting because that connection might not necessarily be maintained over time. So propagating stuff, AIDS, actually, that's what you're saying. Propagating stuff through the network is not necessarily a common feature, but it is certainly popular. And yeah, this is how you get things like the 10 degrees from Kevin or 6 degrees from Kevin Bacon or whatever. If you look at human relationships as a graph over the entire world, the longest, shortest path between any two people is estimated to be about 5.5 steps. That means, given an arbitrary person, I will always be able to contact them by going through going through 5 people who personally will know them by the end of it. So like a chain of 5 people connects me to anyone else on the planet. So understanding graphs, I probably should have put in a slide about this, but understanding graphs is really important and useful. They tend to be organized in ways with this thing called a power, that is just the longest. The longest, shortest path is 5.5. So the reason for this, the way that graphs tend to be laid out in human society, and in most cases, are you have very few nodes or very many nodes that know very few people. So if you think about your average Joe might have 10, 15 friends who he can like contact at a moment's notice. And then you get this sort of curve where the further down the curve you go, the more friends the person has, but the less of those people there are. So there are 1 or 2 people on the planet who are insanely connected. They are just these giant hubs of connections. And the reason that 5.5 is so small is all you have to do is hit one of these hubs and you can get anywhere. So think about it like you have a bunch of little dinky airports and then like one really major airport that goes to any place you want. As long as you can get from the dinky airport to the major airport, then you can fly out to anywhere. Predicting trends in social networks is really interesting to people for a number of reasons. You can do epidemiology that way. You can look at how ideas transmit. One thing that's kind of more sinister is you can think about how many people you would need to remove from the network before it becomes disconnected. And that's actually a really interesting thing about the internet. If you were to try very hard, if you were to get like 20, not really to the question, but if you were to get like 20 to 40 computer scientists and give them a month, they could probably destroy the internet because it has a number of these really highly connected hubs that it depends on. So the task we're going to focus on here is, given this sequence of ti and ti plus 1, can we predict the new links that will show up in the graph? So we want to know what connections will be formed in the future. So maybe these are, I don't know, these guys wrote a paper together and all of these dudes wrote a paper together. Well, now we want to predict that these two are going to write a paper together. So we are predicting links that show up in these graphs. So there are a number of ways of doing this. One of these is we just, for every pair of nodes in the graph, we give it a score. And based on that score, we decide that nodes with high scores are more likely to link, nodes with low scores are less likely to link. And we can maybe map it to a probability somehow. So as chat catches up, I guess I'll pose a question. What is a really naive score? What is a really simple measure that would estimate how likely two people are to link to each other? You don't necessarily need to know how the links started. You just know that new links are showing up in this graph, and you want to predict them. Okay, how many links each already has? That is a perfect geography. Okay, cool. So a bunch of good ideas here. How many links each already has is a pretty good naive method, right? If I have a lot of links, I'm likely to accumulate more links. That's just the rich get richer view. That's why highly connected nodes get even more highly connected, is because they have so many friends already that it's easier to get more friends. David and Wyatt say geography and living nearby. And these are really good indicators of whether a friendship is going to form, but we don't necessarily know them from just the graph. So all of the methods I'm going to show you are domain independent. That means they'll work on any graph. But living nearby, you could also say, like, how many neighbors the two things have in common. So one possible score is just how many mutual friends do we have? Like, I am more likely to become friends with someone who I have a bunch of mutual friends. You guys may have noticed this. Like, you're friends with someone and they have a friend, and you sort of cross paths a bunch of times, and then suddenly something snaps and you're hanging out. This is just called common neighbors. Another interesting one is this thing called Jacquard similarity, which basically says it's going to be common neighbors, but we want to weight it by how many neighbors each person has. So if I have 10,000 friends, it's pretty likely that we will have some friends in common. That's way less meaningful than if I have 2 friends and we have them both in common. So this is just common neighbors weighted based on how many mutual friends we have. This is called Adamic Adar. It is a very similar way of doing it. We are going to sum over all of our neighbors and then divide by the log of how many neighbors that node has. So we look at all of our mutual friends and say, okay, we have say we have Ted, who we are friends with in common, but Ted is insanely popular. So he will have a very low impact, but we also have Justin, who has only us as friends. He's probably going to have a very high impact. Yeah, so this is a sort of global look at this. So we're not looking at it from any of the nodes' point of view. We're just looking at the overall graph. There is this thing called the CATS score. Basically, I'm just trying to illustrate all the different ways people have tried to measure this over time. CATS is a more global score. You need in this equation, nodes that have a higher degree, nodes that have more neighbors, will impact the likelihood of us being friends less. So if we have this situation, So this situation where I'm friends with him, and we want to know whether this link is forming between this guy and this guy, he is going to have a pretty huge impact because he has no other friends. If he has a ton of friends, suddenly our mutual friendship isn't nearly as special, right? Like now it's like, well, this guy just talks to everyone. So this log, this little weird symbol here, is the degree. So if his degree is really huge, he is going to contribute less to this sum because clearly he's just got a ton of friends. All right. So CATS is a another metric where we look at the number of paths in between two things. So the number of unique paths we can get through. And CATS is interesting because you have to be able to look at the whole graph to sort of understand CATS. And there's this other one called hitting time, which is the length of time it takes a random walk to get from A to B. So all of these things, I don't know, have differing degrees of accuracy in predicting how likely a link is to form. I wouldn't necessarily recommend memorizing all of these, but they are, I don't know, sort of ways of doing it. Pausing for a second to let the chat catch up on everything. Do we understand why this is an interesting problem and how these metrics would give us like a really rough baseline of predicting when a link is going to form? One of the other things we can do with this is so imagine for a second, this is another interesting thing you can do with this. Imagine for a second you have, we're going to go with terrorists because that's one of the ways I was introduced to this topic. You have a bunch of terrorists, and these guys have very few mutual friends. Like, so imagine, I don't know, if say we go estimate that the odds of these guys forming a link is very low. This is the least likely link to form. And then suddenly it does form. That is something that is worth noting. Something happened that makes this link happen. James is great. I actually think that is probably true. I thought it was 150, might be 250. And it might be worth bringing to someone's attention. So links that are weird, links that should not have formed, are actually kind of interesting. You can also imagine that this graph is computers talking to each other. So like say you're in like at work, and this is the path through the network computers normally take. And then suddenly these two computers that have never talked before start talking. We know from one of these score methods that it's very unlikely that they would talk. Now this is kind of a red flag. Like maybe something weird is going on. Maybe we should look into it. In general, whenever you can estimate the likelihood of something, this also gives you the ability to detect anomalous stuff. So another way to approach this problem is to take all of these scores. And what do we do when we do machine learning? We featureize stuff, right? So we take every pair of nodes, we make a feature vector for it, And we try and classify it as forming a link or not forming a link. So this is the classic like machine learning out of the box. Like this is the classic forcing something into a machine learning format. We find a way to turn it into binary classification. We find a way to featureize the possible inputs. And then we predict, we use a bunch of examples of links that form and not form, and then try and predict what is actually going to happen. One of the huge downsides, one of the huge difficulties of this is most links will not form in your social network. And there's a couple of ways to get around this. I'm not actually sure if we talked about how to deal with unbalanced data. But when I was doing my thesis, I think something like 1% of the pairs of nodes would form a link at any given time. And this makes it kind of hard for your machine learning algorithm to not just get overwhelmed by the 99% that are not forming. So if you want to just throw out a bunch of your training data, you can do that. So basically, you just throw out most of your data so that all of your number of links that are forming and the number of links that are not forming are equally balanced. And when I say number of links that are forming and number of links that are not forming, I mean examples of times people became friends and times people did not become friends. Or examples of when two computers talked to each other or when two computers didn't talk to each other. As you can imagine, most computers don't talk to each other. So there's a lot more examples of those things. You can also, if you want, clone the smaller class. So you can just copy over and over all of your information on nodes that are forming links to get a higher amount. Or a lot of the time, you can just tell your algorithm, hey, the shit I'm about to give you is super unbalanced. So that's like the very basics of link prediction. We have some pair of nodes. We want to know whether or not they're going to form a link. The most naive way is something like the number of neighbors between the two, or the number of neighbors weighted based on how many common neighbors weighted by how many neighbors. You can also try and view it as a binary classification problem. One of the interesting things, though, that you can do, and this is what my thesis was about, is look at each actor in the network, each individual node, as having its own properties. David, you actually just throw things out until you have an equal number. Like what I actually did for my thesis was I threw out all the examples of not forming links until there was about 200 of each, and then I was like, done. The downside is you're throwing away valuable data. So So one of the interesting things I found about this is these graphs end up behaving in pretty predictable ways. In general, humans are pretty unpredictable, but when you get large groups of them, the overall trends get really easy to predict. So as an example, if I have a vat of molten metal, right, and I'm looking at it from the atom perspective, I'm going to be really like, I have no idea what one atom is going to do. It's going to bounce around and be crazy. But if I look at the vat as a whole, the entire behavior will, the metal will solidify in a really predictable way. So one of the cool things about social network analysis is if you look at it from a large enough scale, people get really predictable. And I think this is pretty fascinating. It's actually a lot like how quantum physics works, right? Like one electron by itself, who knows what it's going to do? 10 trillion electrons, yeah, of course we know what that's going to do. That's really predictable. If I put 10 trillion electrons in a jar, they'll explode and kill everyone because they're just electrons by themselves. So one of the other techniques that you can do for link prediction is modeling each individual node. Yes, you can actually do link prediction between large groups, and that's way easier. So it turns out there are some structures that just show up commonly, and they commonly become other structures. So that guy can frequently go to that guy, and maybe some other percent of the time, oops. I don't know, maybe some other percent of the time you end up with this. One of the things that scientists can do is they basically give these little shapes names and then use them in like a Markov process, saying like, okay, we're going to name this shape, I don't know, the angle. And angles usually either become triangles with like maybe 90% certainty, or I don't know, maybe everyone just hates each other. Shitty triangles with 10% certainty. And you can sort of get an idea from how these little shapes interact with each other. And these are called graphlets. So I don't have a full-size lecture on this, though I could probably talk about it all day. The details get pretty esoteric. But it is a really cool task. I think anything that involves computers and sociology is really interesting. And it turns out that people are pretty predictable. Someone out there probably has a better idea of who your friends are going to be next year than you do. So yeah, I will see you guys next class. I wonder if I can bring a whiteboard to the ice cream cottage. Graphlets are like a very specific new algorithm that people are working on. No, probably they are different from graph to graph. You would have to learn them. Yeah, I'll send an announcement about next class. And good luck on all of your finals, guys.